Hello and welcome to MT3. In this tutorial, we'll be looking at eigenvalues and eigenvectors. We are now in Riley, Hobson and Ben's Chapter 8, Section 13. That's 8.13. Now, before watching this tutorial, I would like you to watch the tutorial on the same topic by 3 Blue 1 Brown. It is linked on the course website, and you can find it on YouTube. And if you haven't watched it, please stop this here and watch that one now, because it does give you a very geometric and intuitive understanding of what we are on about. Okay, let's proceed. So I'm going to assume you have seen that. Now the word eigen here, I'm not sure I'm pronouncing it properly. It means proper or characteristic. Now what we are so these are the special vectors x, such that when your linear operator a hat operates on x, we get back x with some scaling factor here. Now this scale factor could be real or complex, positive or negative, it doesn't really matter, as long as it's in general it's a complex number. So x is in effect unchanged except for its magnitude by this linear operator a, and that's what makes x special. Now in Dirac form we would write this as the operator a, and then we have the ket x, and that's equal to, I won't use color for much more than this, but let's keep the color for now. That's equal to lambda times the ket x. Okay, now that's in the abstract sense. Now in matrix form, this would take the form, let's use color once more. The matrix A operating on the vector x, that's equal to lambda, the scalar, times the vector x. Okay, so this is, of course, just to remind you, you get the matrix form, the matrix vector form, on the introduction of a basis. So on the introduction of a basis. And once again, although I am not going to specify what the matrix looks like, keep in mind that the terms in the matrix and the terms in these vectors will change depending on the base set. If you change the base set, they will change. Now, in fact, we will see more about this when we later on in this series, when we look at what's called a similarity transform. Okay, now the first observation I'd like to make is, observation 1 is that the matrix A is square. Alright, so how do you see that? Well, let's have a look at this matrix vector product. If A was not square, if A was n by m, then the only way in which we could have A operating on x is x itself would have to have as many in its column. There would have to be as many columns in A as there were rows in x. So x would have to be of dimension m. Then you would sum over the columns of m times the rows of x, and this would give you an object which had to be of length n. But x appears on the other side too, so we must have m is equal to n, otherwise we won't be able to have such a relation. So A is square, and in general we'll take it to be some n by n matrix. Okay. The next thing is that this equation is not unique. I mean, x as given here is not unique, because if I took x and I multiplied it by any scalar mu, so mu x, then mu x, if I call this thing x prime, will also satisfy this relation. Let's see why. So A operating on x prime will be A, the matrix A times mu x. Now mu is a scalar, so the matrix doesn't, we can pull it out of this operation here. So this will be mu times A operating on x. A operating on x is lambda times x. So this will be mu lambda x, and now we can bring the mu back in and bring the lambda out. That's mu x, which is equal to lambda times x prime. Okay, so if x is an eigenvector, that means it satisfies this relation, then x prime, which is equal to some scalar mu times x, will also be an eigenvector. Now this would mean that given any eigenvector, you will have an infinite number of these, an uncountably infinite number of these, which would satisfy this relation. This just makes the maths a bit silly, so what we're going to do is work with only normalized eigenvectors, which means we don't care about mu, we just want this length of this thing to be 1. So to make to sort of consider only the interesting cases, we are going to use, I'm going to put this here, therefore use only normalized vectors. Okay, and just to remind you, if you were given any vector x and you wanted to normalize it, then you have to divide x by its norm, which is x divided by the square root of the inner product of x with itself. All right, good. So with those few ideas in mind, let's start our first question. And in this first question, it's a simple one. So here's the question. And this is in fact solved in Riley, Hobson and Benz, so you will find out more. I mean, just have a look at it if you want to see their version of the solution, but it's exactly what I'm going to write down here. So given a non-singular matrix, so non-singular matrix A with eigenvalues lambda I and eigenvectors xi. Okay. Right. That brings me to a bit of notation, which I need to explain in a second. Show that A inverse has the same eigenvectors but has eigenvalues one over lambda I. Okay, so that's what we need to show. Now a bit of notation here, so let's use a blue thing here. Now in general, a matrix A or an operator A matrix A will have more than one set of eigenvalues and eigenvectors. So we need some way of writing these down, and the way we do it is as follows. We use the x symbol, but you don't have to use x, but I'm going to use x here, and the superscript I refers to the which eigenvector is this. So this is the ith eigenvector, and this will be equal to lambda. Now we need an I, and we're going to put this in the subscript now, times the ith eigenvector. So this is for the ith eigenvector. And this is the notation Riley, Hobson and Benz uses. The reason for putting the I in the superscript is so that when we look at the components of this vector, the components, remember, will go in the subscript. Then we don't have a collision of these indices. And for lambda, we put it in the subscript so that we can raise lambda to a power, as we will do later in some examples. Okay, so this is a bit of notation. I'll just box that. Right, so let's come back to this problem now. Alright, so what we do know is that A is non-singular. Now what non-singular means, by the way, if just remind you this non-singular bit here, it means that the determinant of A is not equal to 0, therefore A can't have an inverse. So that's one of the important bits. Because of A is non-singular, so A is non-singular, therefore, let's write the 3 dots, therefore A inverse exists. Alright, so that's the first thing we note. The next thing then is the eigenvalue problem for A itself. So we are told that A xi is equal to lambda I xi, and these are vectors here. Okay, we know that A inverse exists, so let's operate with A inverse on both sides. Okay, so that will give us A inverse operates on the left hand side and it also operates on the right hand side. Okay, you can bring this in. What we end up with is A inverse A. You can see where this is going, I hope, is equal to lambda I is a scalar, so it can be pulled out of this matrix vector multiplication. So we have lambda I A inverse xi. Right, A inverse A is simply the identity matrix, so this would give us an I times xi is equal to lambda I the A inverse matrix times xi. And now I'm going to write this, it's going to come up here. I'm going to write the right hand side on the left hand side, just switch the sides and pull this lambda I to the other side. Therefore A inverse matrix xi is equal to 1 over lambda I times, now the identity times xi is simply xi, so we'll have an xi here. Okay, and this is exactly in the form of the eigenvalue problem. If I call this, if I call this matrix B, then we have Bxi is equal to, and I'm going to call this 1 over lambda I mu I. No, remember we have to put this in the subscript. This is exactly an eigenvalue problem, but this time it's for the matrix B, which is equal to A inverse, and the eigenvalue is 1 over lambda I mu I, which is 1 over lambda I, and the eigenvectors are the xi's as before. Therefore A inverse has eigenvectors xi and eigenvalues one over lambda I, and we have proved the result. All right, there we are. What else would we like to show? Well, the other thing I'd like to show now is that if we are dealing with special matrices, Hermitian matrices, then these eigenvalues and eigenvectors behave in a very special way. So what I'm going to do next is show this for Hermitian matrices, then I will stop this video, and then in the next video show it for normal matrices. We'll come to that. If you've forgotten what normal matrices are, have a look at the previous videos or earlier sections in Riley, Hobson and Benz. So now let's work with Hermitian matrices, and this is quite special, so let's give it a nice red color, or blue. I like blue. So To remind ourselves what is the Hermitian matrix, so if A is Hermitian, then A is equal to the matrix A is equal to the matrix A dagger. Yeah, or in operator form, the operator A is equal to the operator A dagger. Right. So let's start with now we can prove this result both using matrices and operators. I'm first going to use the matrix form. So the first thing I'm going to prove is result number 1. Show that the eigenvalues of a Hermitian matrix are real. Now this is quite an important result. Let's before we so what I want to show here is that if you use the matrix form, so let's draw a line here. Okay. So what we want to show is that if A is Hermitian and if AX is equal to lambda x, let's put an I somewhere here and put an I here and here, then lambda I is real. Now what does that mean? It means that lambda I is equal to lambda I complex conjugate, okay, i.e. lambda I belongs to the set of real numbers. Now how do we show this? Well, let's think about it. Okay, so I can take this equation over here and I can take its adjoint on both sides. Okay, so if I call this equation A, no, let's call it equation 1. Oh, that's a 1 there. Okay, call it little a. Take the adjoint of A. What that gives us is A xi dagger is equal to lambda I xi dagger. Now remember what the adjoint does. If you have the product of two objects, the adjoint will swap them. But of course, if one of them is a scalar, it doesn't really matter which way it goes. And then each of the objects gets adjointed in turn. And a scalar, of course, would the adjoint of a scalar is simply the complex conjugate. Okay, so therefore this becomes xi adjoint A adjoint. That's equal to lambda I star, because the adjoint complex conjugates that, and then we will have the vector xi adjoint. Notice I'm putting a parenthesis around the xi. It's because I already have a superscript here, the I, and I don't want to confuse it with the adjoint. That's why I put the parenthesis there. That's no other reason for it. To me, that's a nice way of handling multiple superscripts. Okay. Now what you can do is now take the inner product, multiply this equation on the right hand side. So from the right hand side with xi. Okay, and what that gives us is now one second, A adjoint, well, A is Hermitian, so A adjoint is simply A. I've used this. So that becomes A, and then we have xi from the right hand side. That's equal to lambda I star xi adjoint xi. Okay, I'm going to call this B. Now what I'm going to do is take A and multiply it from the left with xi dagger. I should have done it earlier, but we can do it now. Take A and multiply from left by xi dagger, and that will give us, so let's have a look at A multiplying on the left with xi dagger, we'll have xi dagger A xi is equal to lambda I xi dagger xi. Okay, now if we call this equation C, and if I compare B and C, we look at the left hand sides, they are the same on both of them, therefore the right hand sides must be equal. So from B and C we get lambda I star xi dagger xi is equal to lambda I xi dagger xi. Okay, and now if I subtract one side from the other, therefore lambda I star minus lambda I times xi dagger xi is equal to 0. Okay, so if these xi vectors are not the 0 vectors, then we cannot if xi is not the 0 vector, then this product of xi dagger xi will never be 0. Therefore we must have this is 0, lambda I star is equal to lambda I if xi is not equal to the 0 vector. Yeah, and in fact, although I haven't said it yet, and I'm going to say it now, what we always assume when we look at eigenvalue problems, such as this one here, we will always assume that these vectors x are never the 0 vector. Because if x was the 0 vector, then this relation would be true for any lambda. It wouldn't really matter what lambda was. You have an infinite number of possibilities. And that's the trivial solution. So there was here a 0th condition, x is not 0, as this is trivial, or as 3 blue 1 brown calls it, the boring solution. We don't want x to be boring, so we will exclude this possibility, and because we've excluded that possibility, when we come down here we don't have xi is not going to be the 0 vector, so this in fact is the inner product. If you think about it, xi dagger xi is the inner product of xi with itself, and this is just a number. This number will never be 0. It's the length of xi. Therefore we must have lambda I star is equal to lambda I, or in other words, lambda I is real. Okay, so that's the proof using matrix notation. Now you can do the same thing using, I'm going to use a different color for this, using the Dirac notation. Now in the Dirac notation we deal with operators. We don't have a basis set, so we have the operator A is equal to A dagger. Yeah, that's our relation we've got down here, up there. Now we use the Dirac notation. So in the Dirac notation the eigenvalue relation is written as A x I is equal to lambda I xi. This time I can drop the bars from on the dx, because if an object is in the ket, then it has to be a vector. I mean, we know it's a vector. All right, so now what I can do is immediately take the inner product of this is relation A. I can take the inner product with xi. Now we take the bra xi. Yeah, so this will give us xi A xi is equal to xi lambda I xi. Now lambda I is a scalar, and it happens to be, it operates on the xi, on the ket xi, so lambda I is effectively in the ket side, and we can just pull it out. So that's equal to lambda I inner product of xi with xi. Okay? Now what we can also do, so I'm going to call this B. We can also take equation A and take the adjoint of both sides. Take the adjoint of A. And this will give us the adjoint converts a ket into a bra vector, and it takes, and we have to have the adjoint of the operator itself, so we will get this. That is equal to, now the adjoint on the right hand side, it will complex conjugate the lambda I and convert this ket into a bra. Now if you look at it here, if this is looking a bit abstract, compare this equation here with this one here. It's the same thing, isn't it? Here I've got the adjoint of the column vector xi. Here I've got the bra form of the vector. Here I've got the adjoint of the matrix. Here I've got the adjoint of the operator. Here I've got the complex conjugate of lambda I. Here it is. And here's the adjoint of the vector xi, and here's the bra form of that vector. All right, now we take the inner product with x, with the ket xi. Okay, so what we get then is xi A hat. Look at this, there's a dagger there, but we know, because this is a Hermitian operator, that A dagger is equal to A. So this becomes so we drop the dagger. xi is equal to and I can pull the lambda I out over here, so let me do that. It's a scalar, so it's already been adjointed. Okay, and I'm going to call this, so we have used, I'll put that in red. Right, put this away. Yes, I know I have a group meeting, and we'll call this equation C. So compare B and C as we did on the left hand side, and what we get is we've got xi A xi, xi A xi, and here, and so on both equations have it, therefore we must have their right hand sides being equal. Therefore lambda I xi inner product with xi, which is just the length squared of xi, is equal to lambda I squared starred dot xi, xi, and therefore, and do the same thing, lambda I minus lambda I star xi in a product with xi is equal to 0. Since xi is not equal to, so the ket xi is not equal to the 0 vector, therefore the inner product xi is greater than 0. So we can cancel it out. That's the only time, this may sound a little pedantic, but the only time you can say conclusively that this equation implies that lambda I is equal to lambda I star is you can only say that if this inner product is non-zero, and this is what we have to show. So this is an important step. Normally the inner product of a vector with itself is greater than or equal to 0. Here we have said it's greater than 0. There is no equality. I forgot this. This is not equal to that. That's important. And therefore lambda I is equal to lambda I star, and therefore lambda I belongs to the set of real numbers. Okay, so we have shown an important result. We have shown that the eigenvalues of a Hermitian matrix or Hermitian operator are real. And this is quite important. Now you might say, where do we use such an seemingly abstract relation? I'm going to end this particular segment of the video at this point. Well, we see it when we look at your Schrodinger equation. There we have the Hamiltonian operating on your wave function gives us an energy times the wave function if you have a time independent Schrodinger equation. And we happily say that these energies must be real. So the energies E belong to the set of real numbers, and that's because this Hamiltonian is Hermitian. And why is it Hermitian? Well, we're going to show this when we look at function spaces. So keep that till any questions you may have, we'll answer them more when we get to function spaces. Okay, so the next thing I'm going to be doing is to examine the eigenvectors of a Hermitian operator. So if you have a question now, what about the eigenvectors of a Hermitian operator? Alright, but I'm going to pause this now because I have a group meeting coming up.